It's really been wonderful to participate in this symposium and attend the excellent talks by students, young faculty and invited speakers. So my talk is on some matching problems. So these problems are quite easy to define. Our input is a bipartite graph where the two sides were traditionally called men and women, but let's call them agents and jobs. So let's say PhD students and teaching assistantships. Every student is adjacent to those TA-ships that she considers interesting and relevant. And she also has a ranking on this is her top choice, this is her second choice, and the other course, there's no overlap of interest at all. Symmetrically, the teaching assistant positions also have a ranking of all candidates that have applied. And so our input graph looks like this. Every edge has a pair of ranks that the endpoints have given each other. And this is a really old and well-studied model seen in many real-world applications. And what we seek here is a matching of agents to jobs. So what's a matching? It's a subset of the edge set such that at most one edge is incident to any vertex. So as in this example, the red set of edges is a matching, so is the blue set of edges, which is a better matching. So let's remember, vertices have ranks or preferences. So we want to find the best possible matching as per these ranks or preferences. The classical notion of optimality in this setting is stability. A matching is stable if there is no edge that blocks it. An edge AB is said to block the matching if both A and B prefer each other to their respective partners in the matching. For example, the red matching is stable. We can check that no edge blocks it, while the blue matching is not stable. The edge between these two, the middle vertices, blocks it. Each of them would rather be matched to the other vertex than to their current partners. So is this a lucky example where there was a stable matching? Actually, it's a very famous result by Gale and Shapley from several years ago that stable matchings always exist. Moreover, they gave a very efficient algorithm to find one. So this algorithm is from more than 60 years ago. These sketches are from 2012, where Shapley and Roth were given the Nobel Prize in Economics. So Roth applied this Gale-Shapley algorithm to many real-world problems, and these sketches are from this website on how a matchmaking algorithm saved lives, in fact thousands of lives, in the assignment of new doctors to hospitals and in helping kidney transplant patients find appropriate donors. So this Gale-Shapley algorithm is a truly simple and clean algorithm. It can actually be described in 5 words: agents propose and jobs dispose. So let's run it on this simple example on 4 vertices, 2 agents, 2 jobs. So both the agents A and S have B as their top choice. So both of them propose to B. B prefers S to A. So for now it accepts the proposal of S and rejects the proposal of A. A unfortunately has no one else to propose to, so that's it. The algorithm terminates with this single edge. There could be an exponential number of stable matchings in the given graph. Interestingly, all of them have the same size. Furthermore, all of them leave the same vertices unmatched and the same vertices matched. And as we saw in this example, the size of a stable matching could be only half the size of a maximum matching. The black matching is a maximum matching here of size 2. But since we were looking only for stable matchings, we have this matching of size 1. So the student A is left with no TA position, the course T has no TA. So by asking for stability, we compromised on the size of the matching. And in virtually all applications, we seek large matchings. In matching students to schools, in residents to hospitals, doctors to hospitals. So by asking for a matching with no blocking edges, by forbidding blocking edges, we have suffered with respect to the size of our matching. So one may say, these are the drawbacks of stability. Size could be only half the size of a maximum matching. Can we relax stability? Can we somehow shift the focus from empowering every edge with a veto power to block matchings, to something more democratic, to some collective decision making. So stability really is a situation where every edge has the power to block a matching. So this motivates something more democratic, which is the notion of popularity. So what is really a more democratic notion? Let's do it via elections. So any pair of matchings can be compared by holding a head-to-head election between them, where the people, the vertices, they are the voters. So let's ask each vertex, are you happier in the red matching or the blue matching? And cast your vote appropriately for whichever matching where you get a better partner. So let's compare the red and blue matchings. The two top vertices are indifferent between the two matchings. They get the same partners in both. The two middle vertices prefer the red matching, and the two bottom vertices prefer the blue matching. So this election is a tie. Let's bring in a third matching, the green one, and let's have an election between the red and green matchings. The green matching loses this election. It gets only 2 votes while the red matching gets 4 votes. So red is better than the green matching. A popular matching is one that does not lose any election. So the green matching for sure is not popular. Whether the red and blue matchings are popular or not, that needs to be checked. So this notion of a candidate who does not lose any election is a really old concept dating back to the Marquis of Condorcet from the 18th century. So he's a French philosopher and mathematician who studied election systems, and he came up with this notion of a true winner. A true winner is someone who can defeat every other candidate in their head-to-head election. So let's look at this simple example. There are 3 candidates, A, B, C, and 30% of the voting population has A as their top choice, B as their second choice, and C as their third choice. Another 30% has the order B, A, C, and the remaining 40% has the order C, A, B. The claim is A is the Condorcet winner here. So how do we check that? Let's hold a head-to-head election between A and B. A gets 70% of votes. And let's hold a head-to-head election between A and C. A wins 30% of votes. So A defeats each of the other candidates in the head-to-head election between itself and them. So what we are asking for is not quite a Condorcet winner, but something slightly weaker, called a weak Condorcet winner. We don't insist that our candidate actually wins every election. We are happy even if it's a tie. So as long as it does not lose an election, that's our winner. So that's a weak Condorcet winner. Unfortunately, even a weak Condorcet winner need not always exist. This is what is called the Condorcet paradox. So let's look at this example with 3 candidates A, B, C, where 1/3 of the voting population has the order A followed by B followed by C. Another 1/3 has the preference order B followed by C followed by A, and another 1/3 has the order C followed by A followed by B. So we can check that there is a cycle. A defeats B, B defeats C, and C defeats A. So asking for a Condorcet winner or a weak Condorcet winner is asking for too much. Such a candidate need not always exist. So let's go back to our setting. We're talking about matchings in bipartite graphs. So a matching is a weak Condorcet winner if it either wins or ties in every election. So is there some more structure in our setting where we can say weak Condorcet winners always exist and those paradoxes that we saw in the previous slide don't occur in our setting? And interestingly, the answer is yes. We have good old stable matchings here in our setting. And it was observed by Gardenfors about 50 years ago that every stable matching is a weak Condorcet winner. So it's just literally a one-line proof. Let's consider a head-to-head election between a stable matching S and any matching N. If a vertex puts its vote in the bucket of N, its partner in that matching N has to put its vote in the bucket for S. Otherwise, we would have a blocking edge contradicting the stability of S. So, the total number of votes for the rival matching is at most the total number of votes for our matching. So, it cannot defeat our matching. So, popular matchings are nothing but matchings that are weak Condorcet winners, and we know it's a non-empty set. Every stable matching is an element in this set. So let's tick the boxes. The very definition of popularity shifted the focus from veto power to something democratic, some collective decision making. And indeed, every stable matching is popular, as was known almost 50 years ago. And in fact, we can show that stable matchings are minimum size popular matchings. So indeed, they allow for matchings of larger size. So the whole story was to somehow ask for a larger set of matchings, matchings whose cardinality is larger than the cardinality of a stable matching. So what we want is an efficient algorithm to find a maximum size popular matching. We know how to find minimum size popular matching. The Gale-Shapley algorithm does it for us. But what we want is the other end, maximum size popular matching. Is there an easy algorithm to find such a matching? So this is an interesting example. When we run the Gale-Shapley algorithm here, we find a pair of the two horizontal green edges. So either the horizontal pair or the vertical pair, both of them are stable matchings here. So there are popular matchings of size 2. Those are stable matchings. And the red matching is also popular. The 4 red edges form a perfect matching, and that's a popular matching. That could also be checked. But curiously, there is no popular matching of size 3 here. So what would really have been a first attempt at finding a maximum size popular matching? Let's start with a stable matching and look to augment it. Look to increase its size by 1. That approach does not look promising because we'll take a stable matching of size 2, these 2 edges, and we could check all possible augmenting paths. None of them results in a popular matching because there's no popular matching of size 3, and we may think, well, perhaps this is the largest size popular matching. So we need something more global. Can we use the amazing Gale-Shapley algorithm somehow? But stability and popularity seem fundamentally different. For example, to check if a given matching is stable is quite easy. We just go edge by edge and check. Nothing blocks a stable matching. Whereas popularity, checking for it seems like a monstrous task. We have to compare our matching with exponentially many matchings in the graph. So let's go back to our earlier example where we ran the Gale-Shapley algorithm and we got this matching, the blue matching. Now our goal is to find the black matching. That's a maximum size popular matching here. But running the Gale-Shapley algorithm is going to give us the blue matching. Can we design a new graph, let's call it G prime, such that the black matching is the stable matching in that new graph? So suppose we replace every edge by 2 edges. So let's duplicate every edge. Let's color one red, one copy red, one copy blue. So the given graph just had single copies of all edges. The new graph G prime, we've replaced every edge by this pair of red-blue edges. And let's also say all vertices on the left, we call them agents, prefer any red edge to any blue edge. And all vertices on the right, we call them jobs, prefer any blue edge to any red edge. So this graph G prime with preferences looks like this. A prefers the red edge to the blue edge. T prefers the blue edge to the red edge. And let's look at S. Its original preference order was B followed by T. And now it is the red edge to B followed by the red edge to T followed by the blue edge to B followed by the blue edge to T. Is this okay? And symmetrically for the vertex B, its preference order is blue edge to S followed by blue edge to A followed by red edge to S followed by red edge to A. So in the original graph, the single edge SB was the stable matching. In this new graph, neither the red edge SB nor the blue edge SB is stable. So the blue edge AB blocks the first matching and the red edge ST blocks the second matching. What is a stable matching in this graph? So let's run the Gale-Shapley algorithm in this. Both the agents propose along their top choice edge to B. B prefers rank 3 edge to rank 4 edge. So it for now accepts this red proposal of S and rejects A's proposal. Now A has one more edge along which it can propose. That's the blue edge to B. So it proposes along this. And this is a second rank edge. So B prefers this edge to the red edge to S. So it accepts A's proposal and rejects the proposal of S. A then goes along its second choice edge and proposes to T, and T accepts the proposal. Everybody is matched. That's the end of the algorithm. So we get this stable matching. I still use the colors blue and red, but let's ignore the colors because we finally want to go back to our original matching. We get back the matching that we desired. So was this really a toy example? Let's write the pseudocode. It's really as simple as this. Let's construct this red-blue graph where every edge in the original graph was duplicated. Let's run Gale-Shapley algorithm in this new graph and then ignore the colors of the resulting matching. That's our matching M. So interestingly, this gives us what we wanted. The claim is this is a maximum size popular matching in G, and actually we use linear programming to prove its popularity. So this algorithm literally seemed as far away from linear programming as possible, but this is such a powerful and ubiquitous tool. We use it to prove the popularity of M. A very high level proof of correctness is that every popular matching has a very simple and clean certificate of its popularity. So we'll see this more concretely in the second half of the talk. So talking sort of in air, this certificate is sort of encoded in these red-blue edge colors in the stable matching M prime. And in fact, complementary slackness will show that our matching defeats all larger matchings. So this certificate will prove the popularity of M, and complementary slackness will show that it is a maximum size popular matching. Because no larger matching is popular because M defeats all larger matchings. So this is a very high level proof of correctness of the algorithm in the previous slide. And we can come up with the following size guarantee also. Any max size popular matching has size at least 2/3 times the size of a maximum matching. So stability had a guarantee of only half, but maximum size popular matching has a guarantee of 2/3. And this is tight. So in this graph, the red matching of size 3 is not popular. The blue matching defeats it. And running our algorithm in this graph would give us this matching, the matching of size 2. So a maximum size popular matching has such a guarantee, better than that of a stable matching. Nevertheless, it's not as good as a maximum matching. So in applications such as students and TA positions, where we may actually want a perfect matching, even a maximum size popular matching falls short of it. But why stop with just 2 colors, red and blue? Suppose we use n colors, where n is the number of agents. Let's call the resulting graph G star. So for every edge, let's actually have n parallel copies. So for every agent, any red edge is better than any blue edge, is better than any green edge, and so on and so forth. And for any job, the preference order is exactly the other way around. Cyan is the best color, magenta is the second best color, and so on and so forth. And in fact, red is the worst color. And within any color class, it's the same old preference order as given in the input graph. I hope this is okay. So what happens? Let's construct this colorful graph and run the Gale-Shapley algorithm in this graph. Any guesses? What would this matching be? So we computed a stable matching in this colorful graph. Then we just ignore the colors. We forget the colors. What would this corresponding matching be? So this is a popular maximum matching in G. So that is, it is for sure a maximum matching, and it is popular within the set of maximum matchings. So no maximum matching defeats this matching. So in an election system where the candidates are maximum matchings, not all matchings, it's only maximum matchings that are the candidates. This algorithm actually shows that there is always a weak Condorcet winner. It's not clear that there always exists a weak Condorcet winner. We could have cycles as we saw in the simple example. But in the world of matchings, we know for sure that weak Condorcet winners exist because Gardenford showed it 50 years ago, that stable matchings are weak Condorcet winners. But we are not in the world of stable matchings anymore. We've restricted our set of feasible matchings to only maximum matchings. So the fact that there exists a popular maximum matching is not clear. But this algorithm always in fact constructs a popular maximum matching. And interestingly, every popular maximum matching occurs as a stable matching in this colorful graph. So every stable matching in this colorful graph is a popular maximum matching, and conversely, for every popular maximum matching, there is a way of coloring its edges so that it becomes a stable matching in this colorful graph. We used n colors, where n is the number of vertices on the left. So this is as colorful. Exactly. So we get a matching whose size bound is at least 3/4 times the size of a maximum matching, but its popularity gets compromised. So it will no longer be a popular matching, but its unpopularity can be bounded in some way. So this particular matching can be unpopular in the entire set of matchings. It can be highly unpopular. But as long as we restrict our attention to maximum matchings, within that set it's popular. So in applications where the cardinality of the matching is extremely important, we do not want to compromise on the cardinality, this would be an appropriate matching. So actually, popular matching algorithms were first studied not in this two-sided preferences model, but in the model of one-sided preferences. So vertices on the left were called agents, and those on the right were called items or objects. So it's only agents that have preferences, items have no preferences. So you could think of this as students and hostel rooms. Hostel rooms don't care who is staying in the room. It is students who have preferences over hostel rooms. So this model is also called the house allocation instance. So it's people and houses. And here, when we compare two matchings, it's only vertices on the left, agents, that cast votes. And so let's look at an example here. So there are 3 agents, 3 houses. So I've basically indicated 3 perfect matchings here, the red, blue, green matchings. So let's hold elections between the green and blue matchings. The green matching wins this election against the blue matching because it gets 2 votes, the votes of A1, A2, and blue gets only the vote of A0. The B vertices don't vote at all here. Let's hold an election between the red and green matchings. The red one wins this election, and in the election between the blue and red matchings, the blue one wins the election. So we are back to the Condorcet paradox. in the model of one-sided preferences, we can have cycles among matchings. So for every matching, there's a more popular matching, and this instance has no popular matching. So this is a natural problem. Given an instance with one-sided preferences, does it have a popular matching? So ages ago, so I was in IAC then, we had an efficient algorithm to solve this problem. But unfortunately, this does not generalize to the popular maximum matching problem. So I was motivated to work on the popular maximum matching problem during COVID times. So there was this news article I read about doctors working in private clinics also have to register with hospitals because hospitals were really short on doctors. And then I thought it's cardinality of the matching that's the most important thing here. Of course, nobody asked me for popular matchings, but I felt, popular matching doesn't solve this problem. What we want here is a popular maximum matchings. So hospitals don't really have any preferences. They're desperate. They want doctors. But doctors have preferences. So the most important attribute here is the cardinality of the matching. We're interested only in maximum matchings. Among them, how do we choose? Let's go based on the popularity. Let's go for one which keeps doctors as happy as possible. And then I realized that our previous algorithm does not generalize. Whereas in the two-sided world, going from 2 colors to n colors was a very natural idea, and it's so nicely generalized from popular matchings to popular maximum matchings. But in the one-sided world, that didn't happen, which made me feel that probably there is yet another algorithm for this problem. This was a purely combinatorial algorithm, a very simple combinatorial algorithm. But now with the experience of the two-sided popular matching problems, maybe there is a linear programming inspired algorithm which is yet to be discovered, and that may generalize to solve this popular maximum matching problem. And indeed, that was the case. So our problem now is find a popular maximum matching in G if there is such a matching. And in fact, we can assume without loss of generality that G has a perfect matching, one that matches all vertices. So we can just add some dummy agents and artificial items. So this is the problem we're interested in. Given an instance with one-sided preferences, does it have a popular assignment or a popular perfect matching? And in fact, we can show this a generalization of the older problem, the popular matching problem, and we'll use linear programming. So the algorithm will be combinatorial, you'll see it soon, but it's motivated or it's inspired by the linear programming method. So how does the LP method work? Let's first look at the following problem. Suppose we are given a perfect matching. How do we test if it is a popular perfect matching, a popular assignment or not? So corresponding to the matching M, there is a nice edge weight function that we can define as follows. Give an edge weight 1 if A prefers B to its partner. Every vertex has a partner, it's a perfect matching. Give it the weight -1 if it prefers its partner to B, or give it the weight 0 otherwise. So the way this edge weight function has been defined, for any perfect matching, its weight under this edge weight function is the difference in the number of votes that it gets and M gets in their head-to-head election. So M is popular, this perfect matching M is popular if and only if every perfect matching has weight at most 0 under this particular edge weight function. And since the way this edge weight function has been defined, the weight of the matching M itself is 0, M is popular if and only if it is a max weight assignment under this particular edge weight function. Now this linear program is easy to write. It's a very simple linear program. So this is the bipartite perfect matching polytope constraints, and the objective function is find a maximum weight matching. Find a maximum weight perfect matching. So M is popular if and only if the optimal value of this linear program is 0, which means every assignment has weight less than or equal to 0, so nobody beats M in their head-to-head election. Now the dual LP will be really useful to us. It's a very simple LP. Every edge has to be covered in some kind of, in an intuitive way. So we have to come up with y values for vertices so that for any edge, some of the y values of its endpoints is at least the weight of the edge. So we can analyze this LP further and show such a claim. The perfect matching M is popular if and only if there is a dual feasible solution such that the objective function value is 0 and all the y values are integral and they lie between 0, 1 till n minus 1 for agents, and they are the negatives of these values for the objects or items. So such a dual feasible solution will be called a dual certificate. So a matching or a perfect matching M is popular if and only if there exists such a dual certificate for M. So in fact, we can interpret these values as colors. So going by our experience on the two-sided popular matching problem, this is nothing but a coloring of vertices, and for any agent, let C star A be the highest color among its neighbors. So based on this color function C and this C star values, we can define a subgraph of G as follows. So let's just do it by an example here. There are two agents A1, A2. The highest level of a neighbor of A1 is 2, and for A2, so these numbers 2, 1, 0, they are the colors of these objects, and these are the preferences that the agent has over its neighbors. So C star A1 is 2, C star A2 is 1. Every agent keeps edges to its most preferred neighbors in the highest color class, and it also keeps edges to its most preferred neighbors in one color class below if they are preferred to all neighbors in the highest color class. So these are rules that we come up with so as to make dual feasibility, so as to come up with certain edges whose inclusion in our matching will enable dual feasibility. So in this example, the bold edges will be in our subgraph, the dashed edges will not be. So finally, we have such a characterization. Our given graph has a popular assignment if and only if there is a coloring of objects by these colors, if this subgraph admits a perfect matching, in which case we can come up with y values or dual certificate for our perfect matching as follows. For any agent, take the color of its partner, and for any object, take the negation of its color. That would be a dual certificate. And so our problem is essentially a coloring problem. Come up with an appropriate coloring of objects so that the resulting graph GC admits a perfect matching. And in case G does not have a popular matching, we will not be able to come up with such a coloring function. So our popular assignment algorithm is as follows. To begin with, let's give all objects color 0. Let's look at the corresponding subgraph. Find a maximum matching. If it's perfect, all is well, return the matching. If it's not perfect, there are some unmatched objects, increase their color by 1. And in case someone's color has exceeded the limit, it has become color n, then return no. If everybody's color is within the legal range, then go back to step 2. The subgraph has been updated because some colors have been increased. So the subgraph, the edge set of the subgraph would change. So again, ask for a maximum matching. If it's perfect, great, return the matching. And if it's not perfect, again, increase the colors of unmatched objects, and the algorithm continues. So this is joint work with some of my collaborators. So this algorithm solves the popular assignment problem, the popular perfect matching problem. So eventually, either we find a perfect matching, so either this statement is executed, or the color of some object exceeds n-1, so it becomes n. If a perfect matching is returned, then we can prove its popularity by constructing a dual certificate. And if the color exceeds the legal range, then in fact we show there is no dual certificate that's possible. So that means there's no popular matching in the given graph. And interestingly, when we replace n minus 1 with 1, then we get the popular matching algorithm. So this is, in a way, I feel, the right algorithm, because this is very much in the same spirit as the two-sided popular matching algorithm, where when we used only 2 colors, what we got was a maximum size popular matching, and when we made it n colors, we got a popular maximum matching. And it's the same here. When we use only 2 colors, we get a popular matching. And this algorithm is more general than the previous popular matching algorithm because it works for something called partial order preferences. So in the one-sided preferences model, preferences need not be strict. We could have ties in preferences, and in fact, there could even be partial orders. Our old algorithm from 2007 does not work for partial order preferences, but this algorithm, when we make CB less than or equal to 1, that works for partial order preferences as well. So I feel this is the correct algorithm for the popular matching problem, and it in fact solves a more general popular assignment algorithm, popular assignment problem. So I would like to take the last 5 minutes to shift to a new problem, again inspired by these problems. So the flavor of the season is election time. So let's talk about a problem in computational social choice. So there are 4 voters here, and so there is an election that's going to take place, an election on a specific issue, let's say, and each vertex, of course, can cast her own vote, but she can also delegate her vote to an in-neighbor. So A delegating her vote to B will actually use the arrow directed from B to A for this purpose. That will be more convenient for us to somehow consider that A delegates its vote to an in-neighbor. So A has various opinions of people, so it does not want to delegate its vote to D. In fact, it ideally wants to delegate its vote to B. That's the top choice. Delegating its vote to C is the second choice. Third rank is, so being, in a way, using the green edge will mean she's going to cast her vote herself. So we just introduced that vertex R for the sake of connectivity. R is just a dummy vertex. So the problem is there are 4 voters. Each of them can go and cast their own vote. That's fine. But they also feel some others may be better informed than them. So they have choices in first choice, second choice, third choice is I myself will go and vote. So they have these ranks on in-neighbors. So there are n voters. Every voter considers its in-neighbors to be better informed than herself, and it wants to delegate its vote to an in-neighbor, and it has preferences over in-neighbors. And we cannot have delegation cycles. A cannot say, I'll give my vote to B, and B gives her vote back to A. Then who is going to cast the vote? So we want to forbid delegation cycles, and every vertex should have in degree exactly 1. That's the person to whom she has given her vote to. So what is the structure that we are seeking? Any guesses? So what we are asking for is an arborescence. An arborescence is a directed tree. So it's a rooted directed tree. And for every node has a unique parent. The parent is the person who's going to cast a vote is going to cast her own vote. So in this arborescence, every vertex will cast a vote for all its descendants, because transitively, so if the arborescence has these 2 edges, so maybe we go to an example like this. So let's look at the arborescence given by the solid edges. So A will cast the vote for D, C and B. all its descendants. So there is another arborescence I've drawn here, which is the dashed edges. So which is a better arborescence? So every vertex prefers the arborescence where it has a better parent or better in-neighbor. So when we compare two arborescences, we just ask every vertex, where do you have a better parent? The notion of partners for matchings is now replaced with parents. So every vertex has a unique parent. So vertex A will prefer the dashed arborescence, because in the dashed arborescence, it's giving its vote to C, and she prefers C to R. Giving the vote to R means she herself cast her vote, and she thinks C is better informed than herself. The vertex B is indifferent between the dashed arborescence and the solid arborescence. C prefers again the dashed arborescence to the solid one. D, on the other hand, prefers solid to dash. So everybody has their preferences. And when we have an election between the solid and dashed arborescences, the dashed one wins the election. And the notion of popularity can now be used for arborescences also. An arborescence is popular if there is no arborescence that defeats it. So in our example, the solid arborescence is not popular because the dashed one defeats it. So a popular arborescence, in a way, is a stable way of giving votes, and this is the notion of liquid democracy. So liquid democracy is a notion that has been, in fact, used in several political parties in Europe, in Sweden, in Germany, and in certain decision making in Google also. So rather than everybody go and cast a vote, if we can delegate votes to each other and one person casts a vote for a group of people, that's sort of in a way, that's considered like merging the best ways of both direct democracy and representative democracy. So popular arborescences are useful in liquid democracy. That's an application. But more fundamentally, arborescences are fundamental structures in combinatorial optimization. So does a given directed graph admit a popular arborescence or not? So our graph in the previous slide has actually no popular arborescence. You can check by brute force that every arborescence has a more popular arborescence. So given a graph, does it have one or not? That's a non-trivial question. How do we solve it? Can we borrow any ideas from our popular matchings? So this question was posed to us by some computational social choice people. And in fact, the popular assignment algorithm can be generalized to solve what is called the popular common base problem in the intersection of two matroids. So matroids are really classical combinatorial structures that generalize the notion of linear independence in matrices. And assignments or perfect matchings are common bases in the intersection of two partition matroids, and arborescences, though they may look very different from matchings, at an abstract level, in the notion of, in the framework of matroids, there is a lot of commonality. Arborescences are common bases in the intersection of a partition matroid with a graphic matroid. And we could generalize a popular assignment algorithm to solve the popular common base problem in the intersection of two matroids where one matroid is a partition matroid. So the popular arborescence problem can also be solved in polynomial time. And yeah, so I wanted to end my talk on this. So these are the references. So this is the first paper, and the two-sided popular matching results are from these two papers. The popular assignment problem is co-authored with Tamas Kirai, Yannick Matuschke, Ildi Schlotter, and Ulrike Schmidt-Kraepelin. And the last result on popular arborescences is from this paper with Kaz Makino, Ildi Schlotter, and Yu Yukove. Thank you.